Hi, welcome to the Dynamics tutorials. So in this case we're looking at kinematics with polar coordinates, and we have a platform that's cylindrical, so it's got a little bit of depth to it, but you can't see the depth because the depth is in this direction. And then it has a slot cut in it, and there's a particle that's moving out away from the center towards the edge of the platform. But then at the same time, the platform is rotating in this counterclockwise fashion. So the platform has a theta position in radians that's described by this function, 2t plus 0.5 times t squared. And then the r value of the particle, just the distance from the origin, has a value that's described by this function of t cubed. So time is in seconds, theta is in radians, and then r is going to be in meters. Once you plug it all in, the units will imagine that there's constants that have units such that it works out. And so the particle moves along the slot, the platform rotates. So we want to find the velocity and the acceleration when theta is equal to 90 degrees. So it starts out here, it's going to rotate up. So once this particle is going to spiral out as it rotates up, and when it's up here, we want to figure out the velocity and acceleration. So the first thing we have to do is figure out time. So we plug in that 90 degrees is pi over 2 radians. So plug that into this formula. So pi over 2 radians is equal to 2t plus 0.5 times t squared. Rearrange that so that now looks like a quadratic formula equation. So 0.5 t squared plus 2t minus 1.571 equals 0. Plug everything into the quadratic formula. Negative time doesn't have any physical significance, so only take the positive root, and we'll get that time is equal to 0.6725 seconds then. From there, just like we talked about in the previous video, just fill in this table. So r dot, r double dot, theta, theta dot, theta double dot. So you can see this is a very different problem in the way it's specified, but the approach is the same. So r is equal to t cubed, so plug in your time, get that value. R dot would be the first derivative of r with respect to time, so the 3 comes out in front. It's a derivative with respect to time, so there isn't any additional term that's there. It's just 3t squared. Plug in your time, get that value. R double dot is the next derivative, so the 2 comes out, so it'd be 6 times t. Plug in your value for t. For theta, you know that theta is pi over 2. Then you can do a theta dot, so d theta dt is just going to be 2 from that first term, plus, this is t squared, so that comes out in front. 2 times 0.5 is 1. So just 2 plus t, plug in your value for t, get that value for theta dot. And then take a second derivative, and so it would just be derivative of a constant is 0, derivative of t is 1, and you get theta double dot is 1 radian per second squared. And then from here you just plug in your formulas. So Vr is r dot, and plug it in. V theta is r times theta dot, and plug it in. Calculate your magnitude of your velocity as these two squared added together, take a square root, you get your 1.58 meters per second. And then for your radial and transverse or radial r and theta coordinates for the acceleration, for AR it's r double dot minus r times theta dot squared. Plug it all in, get that value. For a theta, it's going to be r times theta double dot plus 2 times r dot theta dot. Plug it all in and get that value. Square those two components, add them together, take a square root, and then you get your magnitude of the acceleration. So you can see this is a good general approach that works when you have polar coordinates. Doesn't really matter how the problems are specified. Just make for sure that you're able to fill in this table. R dot, R double dot, theta, theta dot, theta double dot. Thanks for watching.